So title of my talk is Constraints on Dark Matter-Neutrino Interaction from 21 centimeter Cosmology. This talk is mainly based on the updated version of this archive paper. And another paper with my collaborators, Dr. Arnab Pal and Professor Supratik Pal, which is in preparation. So first, I will introduce about the dark matter-neutrino interaction model. Then I will show the effects of this interaction in CMB. And further, I will go to my work, that is the dark matter-neutrino interaction on reionization history. And then I will show the results. And finally, I will summarize my talk. So far, we know that the vanilla ΛCDM model of cosmology is a well-established theory of the universe in light of cosmological observations. But apart from that, it has some tensions like Hubble tension, sigmoid tension, where dark matter is assumed to be non-relativistic and non-interacting. However, from particle physics point of view, dark matter, it is often required to interact, dark matter to interact with standard model particle like dark matter baryon interaction in freeze-out mechanism. And another interesting possibility is that the dark matter-neutrino interaction, which is useful for thermal production of MeV scale dark matter. But it is difficult to prove such interaction with terrestrial experiments. But cosmological perturbations may have some imprint on such interaction and possibility to constrain such interaction via CMB power spectra and matter power spectra. So these are the modified cosmological perturbations equations for dark matter massless neutrino interaction, where the blue part are basically the modifications due to this type of interaction. And here the interaction parameter is U. This is a dimensionless parameter, and it basically depends on the cross-section of dark matter-neutrino interaction. Here for our work, we have assumed that it is constant, but in general, it can be a temperature dependent. So the model parameters for this interacting model is the 6 for standard ΛCDM plus the interaction parameter U. So these are the possible effects of this interaction in CMB-TT and matter power spectra. So these are the theoretical plots generated from class for the theoretical values of this interaction parameter. So as we know that apart from gravitational force, the photon baryon fluid can have contributions from the pre-streaming of the neutrinos and the slow clustering of dark matter. So here we can see there is an increase in the peaks in the CMB-TT power spectra. And because of this interaction, it affects the dark matter clustering. It often so that it suppresses the structure at small scale. And there is an oscillatory feature for this particular, oscillatory feature in the matter power spectra for this particular interaction model. So now I am showing the posterior distribution for the ΛCDM plus U model using the Planck 2018 data, and this posterior has been taken from this particular paper, and where it is shown that the 1 sigma upper limit on U is of the order of 10 to the power minus 4. Though this paper has taken a small value of the neutrino of the order of 0.06 eV, but we have checked that if you set the neutrino mass 0, that is for dark matter massless neutrino interaction case, the 1 sigma upper limit still is of the order of 10 to the power minus 4. So from Planck, it is clear that the U equal to 0, that is a non-interaction case, is still valid. But there is also a few chance that is the dark matter may interact with neutrino. So this motivates us to further investigate this particular type of interaction model in other cosmological observations, like 21 centimeter cosmology or from reionization physics. So this is motivates to present my work that so we have done the semi-numerical simulation for our work. And this basically simulation has 3 parts: the n-body simulation, halo finder, and the reionization model. So we first, we have done the simulation in 214 grid size. And the volume of the simulation is 150 megaparsec cube, and the resolution is 0.07 megaparsec. And for our simulation, we have taken the minimum value of halo, which can host the star formation, is of the order of 10 to the power 9 solar mass. And the NIN, the ionization efficiency, we have taken 23.21 for ΛCDM in order to get the correct optical depth, which from the Planck. And we have taken the mean free path for the photons is 20 megaparsec. And this is the linear matter power spectra for different values of U, which we input to the simulation. And this at redshift 124, and this varies the non-linearly into the simulation, and we are taking the outputs at redshift 8. And these are the particular constants which we have used in our work, that is the ionization criteria. So we have used the 50% ionization condition at redshift 8.0. So these are the mean and 2 sigma limits on volume filling factor of the ionized region and the neutral hydrogen fraction from the Planck data. So if we change the 50% ionization condition from redshift 8 to 7, this will definitely affect our result, and still the 50% ionization at 8.0 is still valid from Planck. And the another is that the values of the ionization efficiency, we have taken less than 500 for a conservative limit case. So we know that the ionization efficiency is basically function of the F star and F escape. These are all uncertain parameter, and it may depends on the halo mass and redshift, but in our case, we have taken some constant value. And if for the zero metallicity stars also, the NR can have very high value, but we know that it has very small impact on the reionization. So we have to take that particular limit of NR that is less than 500. So I move to our work plan, that is to generate the linear matter power spectra for different interaction strength U, and put linear matter power spectra as input to the in-body code and run all the 3 simulations and varies NR from 23 to 500 in order to achieve the 50% ionization criteria at redshift 8. So we have done the many simulation, and from trial and errors, we have found these particular values of U. So we can see that if we increase the value of U, in order to achieve the 50% ionization condition, NR has to be increased. Since if we increase the values of U, it will suppress more power in the matter power spectra. So we set that an upper limit, which is of the order of 6.6 into 10 to the power minus 7 from reionization physics. And if we go further from 6.6 into 10 to the power minus 7 to 6.7 into 10 to the power minus 7, it also needs to increase NR by 500 to 510. So we limit ourselves of the order 10 to the power minus 7 in order to get this particular constant. And we also check that for if we set the U of the order of 10 to the power minus 5, in our simulation, no halo has been formed at that particular suppression. Dark matter. Right. So if dark matter interacts with neutrino, so when the dark matter starts to clustering and it form halo, because of this interaction, the neutrino will hamper the structure formation. And because if the power interaction is very high, then the suppression, then it will affect the structure formation even more. And that's why the halo formation will be delayed. And that's why if we are generating the linear matter power spectra for a particular redshift, for lambda CDM case, what will be the power? For the particular type of interaction strength, it will suppress the power. And if you increase the values of U, the suppression will be more.
The power with the dark matter is suppressed and the star formation is suppressed.
Yes. Yes, that's the motivation for our work. So these are some outputs from the semi-numerical simulation. That is this is a nonlinear power spectra generated at 8. So we can see that if we increase further values of U, it will suppress the power. And here we have seen that the no oscillatory features is there as in the case of linear matter power spectra. And the second is the brightness temperature power spectra. And we can see that for lambda CDM model, the brightness temperature power is less. And if we increase the values of U, the matter power spectra will be less, but here the brightness temperature power increases as U increases. So more power at larger U helps to detect the signal. And these are the H1 maps generated at redshift 8.0 for this particular interaction strength and NR. So we can see that this dark region is the ionized region, and we can see that there is less structure forming if we increase the anion. So this motivates us to the next part, that is the detection prospects of this particular interaction. So this is the antenna layout of the SK1 low, which is in Western Australia. And this is the specifications for the telescope. And this is the noise power spectra generated from SK1 low telescope. And we have used to generate this noise power spectra, we have used the cosmic variance from the beam average beam average power spectra. We have not taken into account the trace power spectra. And we also taken the optimistic limit of the foreground model, that it is completely removed after modeling, so that the entire K space is allowed for observation. So this is the comparison of the signal to the noise power spectra, and we can see that there is a signal to noise ratio is of the order of 5, and signal is much higher than the noise power spectra for 0.1 to 2. So it is a possibility to detect the signal from SK1 low observation. So this is the summary of my work, that is the 21 centimeter power spectra can improve the constraint of this type of interaction in a conservative limit, and it can help to detect the signal using this telescope. And another point is that the similar analysis has also been done independently, and they have also found a similar constraint on U, which is of the order 10 to the power -8. This is done by this particular group. And another point I want to make is that since we know that from neutrino oscillation experiment, neutrinos have mass. So we have, for the first step, we have basically doing the calculation of the dark matter massive neutrino interaction from post-deionization epoch. Here also the perturbations equation will be same as the case of dark matter massless neutrino interaction, but it has non-zero mass. And from Planck data also, the interaction parameter, 1 sigma bounds on the interaction parameter is of the order of 10 to the power -4. And here the model parameters are 6 plus U plus the sum over neutrino mass. And these are the posterior forecast for this particular type of interaction model using the SK1 intensity mapping band 1 and band 2 experiment. And for this, we have generated the mock catalog for this particular type of model using this SK1 mid telescope specification. So we have also doing this particular, studying this particular type of model in the other LSS experiments. So this is in progress. So I will like to stop here. Thank you for your attention.
Thank you. Any questions, comments?
So any particular reason you looked only at reionization constraints and not something like Lyman alpha, which would also suppress structure on small scales?
So we are, first we are doing this from the reionization, and we are hoping that we will do from Lyman alpha also.
Are there other constraints on this
Experiments like Zoom?
You're from EU? So as far as I know that from Planck and other Planck plus bow, Planck plus Lenzing also, there is a constraint on U is of the order of 1 sigma bound is 10 to the power -4. Still the U equal to 0 is valid, but 1 sigma from other physics also it 10 to the power -4 of the order.
Just one comment about that, if you go to a parameter U, which was on the previous slide, you had the formula for U, right? Which
Okay.
Yeah. So this is compared to the Thompson cross section,
right? Which
is about a barn, right?
Mm-hmm.
So your cross sections are like, if it's 10 to the -4, you're basically saying it's 10 to the -4 barn. But already from perturbativity, if you have a 100 GeV dark matter, cross section is going to be very small from if it's a perturbatively calculated cross section. So this limit is not really, unless it gets much stronger, right? Like already 100 GeV dark matter with order 1 coupling constant will give you picobarn cross section. Right? So this is not really a very useful constraint because from perturbativity also, you already know that the cross section cannot be large for such a heavy dark.
So you can get constraint on this interaction from relic abundance also. Have you taken this into account because you're considering this interaction? And
I think from the Planck constraints, it also taken into account the relic abundance.
Yes. Okay.
Any other questions, comments? If not, let's thank Antara for a very interesting talk.